welcome back. We're excited today to look back at Theorem 2.9 from Chapter 2 because we're going to use a related result in the determinant conversation coming up. So Theorem 2.9 in particular said something about how you could find the inverse of the product of two invertible matrices. So the proof idea for this went something like we write down the exact inverse of AB. Okay, so really what this does is it uses the definition of inverse, and that's how it proves it's invertible. So I use definition of inverse, and say that AB inverse is actually equal to B inverse times A inverse. Okay. So today what I want us to look at is the converse of Theorem 2.9, which is not logically equivalent, remember, so it's not inequivalent, it's not equivalent. Both could be true, one could be false, both could be false. It's unknown until you actually go through the proof. So for the converse here, we have A and B being n by n matrices. The converse is that AB is invertible, then A and B are invertible. So let's just put this note. So not logically equivalent to Theorem 2.9 because it could be true, it could be false, we don't know. So we have to prove this separately. On its own. Alright, so how are we going to do that? So I want to do it in two parts. So first I want to say if AB is invertible, then B is invertible. So let's start with that proof. So proof, let A and B be n by n matrices. Right. And assume that AB is invertible. Alright, so what can we do with AB being invertible? Ooh, let's go back. Okay, let's prove this converse in two parts. So the first part, we're looking at if AB is invertible, then B is invertible. And what I want to actually do is I want to prove the contrapositive instead. So remember, the contrapositive is logically equivalent to the original statement. So this is equivalent. Let's make that note. So let's just say which is, so if we're proving something by the contrapositive, we should probably write down the contrapositive. Right? If B is singular, then AB is singular. Alright, so let's just go ahead and start the proof. Let A and B be n by n matrices with B singular. Alright, so there's not a ton we know about singular matrices other than the fact that they're not invertible. But actually what that means for us, so by Theorem 2.15, so that was the one that says a matrix is invertible if and only if a ton of other stuff is true, right? So by Theorem 2.15, this means there is a non-trivial vector column matrix, we'll say, instead of vector matrix U, let's remind ourselves it's non-trivial, such that B times U actually equals the 0. Right? So now we want to show that AB is singular, right, from our contrapositive up here. So let's just go ahead and then compute. Right, it's going to fall out very quickly. A times B times U, which is A times BU by associativity. Matrix multiplication, and then that is the 0 substitution. That's a lot of T's. Okay. And then that's A times the 0 matrix, which is the 0 matrix, or we'll put the line above it to say it was the column matrix. All right. So multiplication by 0. Right. So therefore, essentially what was shown is ABX equals 0 has a non-trivial solution. And must also be singular. By Theorem 2.15. Okay. Excellent. So we did indeed prove the contrapositive. Therefore, or let's use a different word. Maybe, I don't know if this is good English. And so, the contrapositive and original statement are true. I'll put a little QED box. Okay. So this proves half of our converse. Remember, we wanted to say that if AB is invertible, then B is invertible, as well as A itself. So let's go ahead and try and prove that A is invertible. And I'm going to do this in a really super duper sneaky way, but it's going to be fun. So converse part 2. Right. So let's zoom in, start writing proof. Hopefully it's short, so let A and B be n by n matrices. We're not going to do any contrapositive or anything this time. Assume AB is invertible. Alright, so we want to show A is invertible. Let me zoom out so that we can see everything. A is invertible. Alright, so we're going to be really sneaky. So by Theorem 2.8, since AB is invertible, its transpose is invertible, which we know the transpose to be B transpose A transpose. I believe that was Theorem 2.6. Alright, so maybe we'll throw this in here, and 2.6. Alright, it's also invertible. Okay. But now we get to be sneaky. So now we have A transpose, a product, which is invertible. So by converse part 1, that means that the first thing, or the second thing, sorry, is invertible, right? So by converse part 1 in this video, A transpose is also invertible. As I said, we're going to be sneaky. We're not going to, yeah, this is going to be fun. Okay, A transpose is also invertible. So therefore, let's see here, by theorem 2.8 again, 2.8, the transpose of A transpose, which is just A, is also invertible. And we call that quits. Right? So nice short proof once we've done the first part of the converse, and we have theorems 2.8 and 2.6, and we can just be a little bit sneaky here. Alright, so let's think about why this matters. So for one, it means that theorem 2.9 can be used for its converse as well. Well, you don't want to say that, but by the converse of theorem 2.9 is definitely a sufficient statement and reference. And moreover, we have this corollary that you've kind of seen sneaking into the video, that if we have some matrix and we can find a matrix B where we can just multiply on either the left or on the right by B to get I, then A is invertible. So the key difference between this and just showing something is invertible is that we only have to check one side. For invertibility. This is a very important fact, invertibility, and will be used a lot. And how does the proof of this go? The proof actually uses the contraposit, or the converse, very quickly. So let's just let A be a matrix. Such that there is some matrix B for which A times B is the identity matrix, okay, which is invertible. So notice AB is then invertible. Okay. So A must also be invertible. By the converse of theorem 2.9. Right. So a similar argument works for BA equal to I. We won't write it out because it is really just the same thing. And we can put our little QED box. All right. So we have a few useful results. So first off, this corollary is going to come in handy a lot. All right. The converse is going to come in handy. Theorem 2.9, of course, is very useful. We've used it many times already. And then the part 1 and part 2 just are part of the converse. So I guess individually they fit into there. All right. So thanks for continuing to watch. Thanks for getting to the end. Congratulations. And have a wonderful day. Bye-bye.